Okay, so I think we're ready to get started. So thanks everyone for connecting to the monthly seminar of the Working Group on Active B stars. This month, it is my pleasure to present Dr. Margaret Lazzarini. Dr. Lazzarini obtained her Bachelor in Astronomy and Physics from Yale University, then started a career as a high school physics and astronomy teacher in Los Angeles, before obtaining her PhD from the University of Washington in Seattle. She was then an NSF Astronomy and Astrophysics postdoctoral fellow at Caltech, and just recently, as of August 2023, started as an assistant professor of astronomy and physics at Cal State Los Angeles. Today, Dr. Lazzarini will be talking to us about multi-wavelength characterization of high-mass X-ray binaries in M33. So thank you very much for accepting our invitation, Dr. Lazzarini, and please take it away.
Great. Well, thank you so much for having me. As Alex mentioned, I'll be talking today about work that I've been doing over the last few years, doing multi-wavelength characterization of high-mass X-ray binaries in M33. And this is work that has only been possible in collaboration with many others, including some students that I have up on the screen here. And especially due to the very multi-wavelength nature of this work of collaboration on the X-ray observations, the optical observations, both space and ground-based. So to start off with a little bit of a roadmap, I'm going to start the talk with some background and motivation just to kind of ground the work, and then get a little bit more in depth about the specific population demographics of the high-mass X-ray binaries that we see in M33, so including characterization of the companion star in the systems, the age distribution and production rates that we can measure in this galaxy, what types of compact objects are likely in these binaries, and then I'll discuss some ongoing and future work, including some work doing simulations of the high-mass X-ray binary population in M33 with binary population synthesis, and an ongoing ground-based optical spectroscopy campaign to get additional data on these companion stars in the binaries. So first off, for background and motivation, I think that, this group, I probably don't need to tell. The first level of motivation for this talk is that massive stars are important, and that is kind of a lot of what I'm trying to study here is kind of understanding massive stars, their evolution, and kind of how they impact their galactic environments. So massive stars are important from many angles. They play a really important role in galaxies. So they inject ionizing photons, chemical enrichment, and supernova feedback. So they play kind of an outsized role in the galaxies in which they live. And all of this is to say that's kind of true for all massive stars. But it's important to note that the average high mass star is actually in a binary or a triple star system. And so we can't really ignore binarity completely when we're talking about massive stars and how they evolve. So when we're looking at a group of massive stars, unlike this cartoon, we're probably seeing something that looks a little bit more like this, showing some stars with companions up to some of them have even 2 or 3 companions. Typically, the higher order multiple systems have one kind of tighter binary. And then a large fraction of these binaries are actually close enough to interact, so to exchange mass at some point throughout their evolutionary process. So we'll kind of revise the initial statement. Massive stars are important, and when we talk about massive stars, we're inherently talking about massive binary stars. So understanding massive binary stars is a little bit complicated. The evolutionary process for binary stars gets more complicated because of processes like mass transfer. So I'm showing here an illustration of one possible life cycle for a massive stellar binary going from the zero-age main sequence, and this specific scenario resulting in a neutron star merger producing a black hole at the end of its life. But as you'll see in this diagram, there's several stages of mass transfer. There are 2 different Roche lobe overflow events. There's even a common envelope here. And then there's mass exchange during one specific phase that I'm most focused on, which is the X-ray binary phase. So that's where one of the stars in the binary has already become a compact object, which accretes mass from a stellar companion. So high mass X-ray binaries, again, can have a black hole or a neutron star accreting mass from a high mass companion star. And the observation of these systems is inherently a multi-wavelength affair because we kind of get different emission from the different components of this binary. So we study the accreting compact object through X-ray emission. We can use softer, so less than 10 keV photons to study the accretion onto the compact object. And in my work, we use Chandra to identify systems at these energy ranges and obtain very precise positions for the location of the compact object. We can also use harder X-ray observations with NuSTAR to start to distinguish between black hole and neutron star accretors based on spectral differences at higher energies between accreting neutron stars and black holes. And then to study the high mass companion stars, we turn to infrared optical ultraviolet emission. So in this work, I'm going to primarily be talking about data with the Hubble Space Telescope that was used to identify and do kind of initial characterization of these systems. And then I'll talk a little bit more about some additional optical data from ground-based spectroscopic observations. And with this optical and UV emission, we can study both the star itself and we can place it in the context of its parent stellar population. So from that, we can infer things like its likely age and kind of the overall ties with the galaxy properties. So one other kind of motivation for studying massive stars is illustrated in this binary evolution diagram, particularly this last two panels of the evolutionary picture here. So some massive stellar binaries could result in new compact object mergers, which in turn would produce gravitational waves. And the detection of gravitational waves from merging neutron stars and black holes has really kind of, I think, reinvigorated a lot of interest into this field of massive binary stellar evolution. And it's cracked open a lot of questions. How exactly are all of these compact object binaries formed? This is a plot showing the masses in the stellar graveyard, indicating gravitational wave detected, black holes and neutron stars in cyan and orange, and black holes and neutron stars detected with electromagnetic radiation, generally in X-ray binaries in pink and yellow. And we know that we now know it's a complex picture. These are not all produced through isolated binary stellar evolution, but some of them likely are. There is also dynamical evolution in dense environments, such as globular clusters. And it's kind of in order to piece together how all of these formation channels contribute to the observed population of gravitational wave sources, we need to understand each channel in depth. And so the work that I am focusing on is tied to this isolated binary evolution channel. The last piece of motivation that I'll say before we get into just the actual meat of studying the M33 HMXB population is that high mass X-ray binaries are also played a likely big role in cosmic reionization. So at redshifts beyond about 5, high mass X-ray binaries actually dominate over AGN in their production of ionizing photons. They can form very quickly on mega-year timescales and are very bright X-ray sources. So to summarize the motivation, massive binary stars are important. They play an important role in the galaxies in which they live. Massive binary stellar evolution is a very complicated and interesting process, and there are many open questions within that process. And high mass X-ray binaries can be progenitors to binary compact object mergers observable with gravitational waves. And high mass X-ray binaries likely played an important role in cosmic reionization. So with all that said, how do we actually go about studying these systems? So there are multiple ways to connect high mass X-ray binaries to binary stellar evolution and to the galaxies in which they live. And so we can, on the left, study integrated X-ray emission from whole populations of high mass X-ray binaries in more distant galaxies and see how that scales with galaxy-wide properties like star formation rate, stellar mass, and metallicity. In the much more local universe, detailed studies of individual systems in the Milky Way, we're able to do more detailed accretion modeling to really understand the specific physics of accretion in those systems. And the work I'm presenting today falls at this kind of middle ground. So the work that I do is focusing on population studies of high mass X-ray binaries in nearby galaxies. So these are galaxies that are close enough that we can identify individual systems. They're definitely not quite as close as the systems in the Milky Way, which makes, the number of X-ray photons we get lower, which makes some of the more detailed accretion physics work more challenging. But the trade-off is we get this population scale view, which allows us to try to start saying something statistical about what we're seeing in these populations. What makes local galaxies such a great place to study these populations is that within the local group, galaxies like M31, M33, the Magellanic Clouds, and other local group dwarfs, is that they're close enough that we can resolve their stellar populations. So I have a video here, which I'll play. Hopefully it is not going to be too jumpy on Zoom. I know that can be an issue sometimes. But this is showing for a survey in Andromeda, so M31, that was collected with the Hubble Space Telescope. So we're zooming in on kind of like a ground-based image, and then we'll transition into the HST data. And as we zoom, you can see that we're continuing to zoom until we can resolve all of these individual points of light that are individual stars making up the galaxy of Andromeda. So this type of observation is possible with many orbits from the Hubble Space Telescope. And this is showing M31, but this is the same data quality that we have for HST in M33. So with these local group galaxies, because we can resolve their stellar populations, we can identify individual stars that are the companion stars in these systems. One other important benefit is that all of the HMXBs are at the same distance from us, so we don't have any of the distance issues that sometimes occur within the Milky Way. We can look at different local group galaxies to see a range of metallicity and star formation rate intensity and how those impact the resulting populations. And I'm just showing here a little inset to kind of show a super zoomed in version. So this is about a 40 by 40 parsec region within M31, showing the type of data that we are working with in that galaxy. So once we have these resolved stellar populations, we can identify the companion star in a high mass X-ray binary. We can characterize it, so using multi-band photometry. We can determine the age of the system using measurements of the star formation history of the galaxy and use that to calculate the production rate of high mass X-ray binaries. So I'm going to go into a little bit more detail on the HMXB population demographics in M33. So we're focusing again on local group spiral galaxy M33, which is 859 kiloparsecs away. This image is a mosaic generated with the HST data that I use in this analysis, taken with the Hubble Space Telescope. M33 is an interesting place to study high mass X-ray binaries because while it's a smaller galaxy, it has a very high star formation rate intensity and a fairly strong metallicity gradient. Although, as I point out in the figure on the right, the radii that we are probing, I think I might have mislabeled this on the diagram, but the radii at which we're probing, we don't get down to the lowest metallicities in M33, but we are hoping in the future to expand our data out to the outer disk, which gets down to closer to SMC metallicities. But this high star formation rate intensity means that even though the galaxy is smaller, it still has a pretty comparable sized high mass X-ray binary population to a much larger galaxy like M31. And it also has been the target of several recent multi-wavelength studies. So in the magenta, I have outlined the footprint of the HST data that we use in this analysis. The Chandra data set is outlined in cyan, and there are also overlapping new star observations for a fraction of our observed field. And just to kind of give a little bit more detail, so we are using Hubble Space Telescope observations from the panchromatic Hubble Andromeda Treasury Triangulum Extended Region, or FATTR survey, which covered the inner disk of M33, providing 6-band photometry from the near IR to the near ultraviolet for over 20 million individual stars. The X-ray data that we're using is the Chase M33 survey, which was a Chandra survey of the full disk of M33. And then we also, I'll talk briefly about some work trying to fold in the higher energy X-ray observations with NuSTAR from the M33 Legacy Survey led by June Yang. And so just to motivate, what do we get out of these different wavelengths of coverage? With Hubble, we are able to identify and characterize companion star candidates, measure star formation histories to get age distributions. With NuSTAR, we get this hard X-ray coverage, which allows us to constrain the type of compact object in the system. And then the key here is Chandra, which really connects the two. So because of Chandra's high angular resolution, we're actually able to identify these optical counterparts in the HST data, and then kind of tie which X-ray source we're seeing with Chandra to the NuSTAR observations. So just to give a little bit of a visual on kind of what this looks like, I'm showing here an HMXB candidate in M31 actually, but with very similar data and process here. So on the left is a 3-band optical image from the HST survey, and on the right is a multicolor X-ray image from Chandra. And the circle indicates the 1 sigma positional error from the Chandra X-ray source. And you can see in the optical image, there's one really bright blue star that is within that 1 sigma positional error, making it a really strong candidate to be the companion star in that high mass X-ray binary system. So to actually go through and select our HMXB companion star candidates, we use a combination of spatial and color magnitude cuts, essentially looking for stars that are within the 1 sigma positional error on the X-ray source position that have colors and magnitudes consistent with being massive stars. So, you know, greater than 6 solar masses, we have some slightly different cuts depending on the amount of dust extinction that we think that we see. So I'm showing you here, this is the same star from the previous slide. You can see the optical image on the lower right. We also have some UV images from HST. So I have a single band UV image on the lower left. You can see that this star is also very UV bright. And then its position on the UV and optical CMDs indicates that it is likely to be a massive star, making it, again, a very good companion star candidate in this high mass X-ray binary system. So we did this for all of the X-ray sources from the Chase M33 survey that fell within the fatter survey footprint. We went through and systematically identified likely companion star candidates, again, using the spatial correlation as well as color magnitude cuts. And so I'm showing here a multi-panel figure with an optical and then also ultraviolet color magnitude diagrams. The background regions on the optical color magnitude diagram indicate where we expect different types of stars to live, just kind of roughly drawn. And then we have our identified HMXB companion star candidates that are color-coded by if they appear to be a likely main sequence star with low dust extinction, so 0 to 1 magnitudes of AV, slightly higher dust extinction, or an evolved, so giant or supergiant star. So this is kind of our initial selection of our companion star candidates. So I'm going to say a little bit more now about how do we go about characterizing these stars once we've selected and identified them. And I want to kind of briefly say, well, what are our goals? What are we trying to figure out about these stars and about this population as a whole? So one thing that we're trying to do is obtain a large, clean sample of high mass X-ray binaries. So as large as we can for a kind of statistical understanding about, you know, how many of different types of high mass X-ray binaries we see. And then also clean. So contaminants that we have in these types of studies can be background AGN that we're seeing through the disk of M33. Sometimes we see X-ray bright low mass stars in the Milky Way's halo. So how do we weed out these sources that could be kind of masquerading as high mass X-ray binaries in M33? We want to characterize them. So we are going to perform some fitting to figure out what is their likely spectral type, which we kind of infer from best fit luminosities and effective temperatures and stellar radii. What are the ages of these systems, which can indicate something about the formation channel, and then the overall production rate of high mass X-ray binaries in M33. For the subset of our sources that have hard X-ray coverage, what types of compact objects do we see? And again, this overall goal is to get a really detailed kind of understanding of this population that we can then compare to simulations to understand and constrain models of massive binary stellar evolution. So in M33, our total sample comprised of 65 high-mass X-ray binary candidates, which I have plotted on this near ultraviolet image of M33. They're color-coded by what type of star we think the companion is in the high-mass X-ray binary system. And as you can see from this image, the majority of them are likely B-type main sequence stars, which we infer from SED fitting, which I'll discuss in just a second, suggesting that the population of high-mass X-ray binaries in M33 is dominated by Be X-ray binaries, which is similar to what's been seen in the Magellanic Clouds. So how do we determine these likely spectral types? We use spectral energy distribution fitting of the HST photometry. So we use this tool called the Bayesian Extinction and Stellar tool, or the BEAST, which fits observed multi-band photometry. We use both optical and ultraviolet photometry, and fits with stellar models, measurements of photometric bias, and dust models to get out physical properties of these stars like mass, temperature, luminosity, dust extinction, etc. So to show kind of an example of what this looks like, this is for one of our high-mass X-ray binary candidates. The 4 black points are our observed flux in the 4 photometric bands that we have. And the blue line is the full stellar plus dust plus bias model that fits to our observed photometry quite well in this figure here. And then we get out of this, we can get out what we think is the star's effective temperature, its luminosity, its stellar radius, how much dust extinction do we think that it has, etc. So we perform this fitting for the photometry of all of our HMXB companion star candidates that we identified using the spatial and color magnitude cuts. And then we can put them onto a Hertzsprung-Russell diagram to kind of show, and then basically where they live on this diagram is what we use to infer whether they're likely an O or B main sequence giant or supergiant. We also include the stellar radius, so there's kind of a third dimension to this classification. But you can see that, again, the bulk of our stars lie in that B main sequence region of our diagram. And again, suggesting that this HMXB population in M33 is likely dominated by BE X-ray binaries, which is what we would expect, especially at kind of the lower X-ray luminosities that we are able to probe in this Chandra survey. So about 76% of our full sample are likely to be BE X-ray binaries or are likely to have B-type main sequence stars. And I say this kind of caveat that obviously these classifications are done with photometric data. We are in process of doing the spectroscopic confirmation that's needed to actually say, are these BE stars? And also to spectroscopically confirm binarity in these systems. So there's still HMXB candidates here, but signs point to a population likely dominated by BE X-ray binaries. I always want to say a quick word about how do we kind of clean our sample. So how do we find the best high-mass X-ray binary candidate sample? And again, our goal is to remove contaminants, so foreground stars, background AGN from our sample. And we use several different multi-wavelength pieces of information to do this. So one thing we do is we compare the X-ray NH column density to the optical AV. We kind of look for correlation there to remove things that appear to not actually be in M33, so things that could be behind the disk of M33. We look at the spectral type from the SED fit. So some of our stars that we did this SED fitting for returned very non-physical fits, indicating that they're likely not stars at all, but probably background AGN. We look at the hardness ratios from Chandra. We expect accreting black holes and neutron stars in high-mass X-ray binaries to be hard X-ray sources. So if we have any sources that are softer than we expect, then it's a likely sign that they could be a foreground star. We also look at infrared colors, which is another great way to remove foreground stars from our sample. And then lastly, we look at the star formation rate in the local region of the M33 where that source is located, and basically try to have some sort of a cut on are these in regions of the galaxy experiencing recent star formation within the last 80 million years? If not, it's more likely that it could be a background source. And in the paper, I go into more detail on this, but it's essentially, we used a system of flags so that a source wasn't immediately cut if it looked suspicious according to one of these different criteria. But if a source raised multiple flags, then it was kind of indicated as likely to not be a good high mass X-ray binary candidate. So I want to move on now to talking a little bit about how do we determine the ages of the high mass X-ray binaries in M33 and the production rates. So we use spatially resolved recent star formation history maps of M33 to constrain the high mass X-ray binary ages. So I'm showing on the left here a synthetic color magnitude diagram that was created as part of the process of fitting the spatially resolved recent star formation history of M33. And this is showing, essentially the idea, we're fitting the spatially resolved recent star formation history with color magnitude diagram fitting. We can essentially look at a mixed age stellar population as a superposition of multiple single age stellar populations on the CMD. And then we can essentially weight, how much we weight each single age tells us something about the star formation rate at that time. And we can do this across the galaxy in different spatial regions. So for the star formation history measurement in M33, I used color magnitude diagram fitting, focusing on main sequence stars to focus on the recent star formation history, and divided the spatial region of that fatter survey up into 2006 individual regions for which the star formation history was measured independently. So in each region, we have a time-resolved measurement of the star formation rate. And then when we look across regions, we have a spatially resolved measurement of the star formation rate. So we produce maps that look something like this on the left, where each pixel in this image is one spatial region of M33 for which the star formation history was measured independently. And you can see from this figure, which combines the star formation rate in the last 79 million years, that we recover the spiral features of this galaxy quite well. So we're able to do both individual regions as well as looking at kind of larger scale changes in the galaxy's evolution over time. So to figure out the likely age of an individual high mass X-ray binary, we look at the star formation history in the region containing that star formation history. And each of these regions here are roughly 100 by 100 parsecs. So for example, we can look at, this is showing the star formation history in one region containing one of our high mass X-ray binary candidates. This is a measurement of the star formation rate over the last 80 million years. And you can see there's a strong peak in the 40 to 50 million years ago time bin. We can essentially figure out, we create a probability distribution for the age of each of our high mass X-ray binary candidates by converting this star formation rate over time to a stellar mass produced in each time bin, and then we turn that into a probability. So we do this for all of the stars in our population, which allows us to create something like the figure I'm showing on the left here. So when we sum the probability distribution on the ages of all of the high mass X-ray binaries in our population, we get this age distribution, which is shown in the black histogram on the left here. The green line is just showing if we do the same analysis, picking an equal number of random regions from the star formation history maps, not focusing on whether or not there's a high mass X-ray binary located in that region. We see that we have this kind of peak above random in both this earliest 0 to 10 million year bin and in this 40 to 50 million year bin. We can then convert this into a high mass X-ray binary production rate when we basically divide by the total star formation rate in the survey footprint over the same time scale. And again, we get these peaks at the 0 to 10 and 40 to 50 million year timescales, which have been seen in other galaxies. The 0 to 10 million years is kind of an expected formation channel for the most massive high mass X-ray binaries. And that 40 to 50 million year timescale has been seen as the likely formation timescale for Be-XRB binaries. And one thing that's kind of interesting in this work, this whole talk is focusing on M33, but as part of my PhD work, I did similar analysis in M31 using very similar HST and Chandra data sets. So we can do a real apples to apples comparison of their high mass X-ray binary populations, looking for things like how do star formation histories and metallicity affect the resulting high mass X-ray binary populations. The big takeaway here is that they look remarkably similar, which is interesting and basically suggests that the star formation history, because even though these two galaxies, the area that we did this analysis in are quite different in scale, because of the higher star formation rate intensity in M33, we're actually looking at a very similar amount of total star formation in both galaxies. And you can see that the high mass X-ray binary production rates match within errors within the last 50 million years and are very close to matching within errors over the last 80 million years. And again, this region of M33 that we probed in this analysis was very close to the metallicity of M31. We didn't have HST coverage in the outer disk where we would get to closer to SMC metallicities. So that's something that we're excited about in future work to kind of extend this analysis to be able to see the impact of the metallicity gradient in M33 on the high mass X-ray binary population. So again, we kind of see this very similar total star formation rate in these two areas of the galaxies that we surveyed. And we see a similar high mass X-ray binary production rate and number of HMXBs observed in both galaxies. So I want to talk quickly about some of the work done to figure out the compact object type in these galaxies. So this wasn't kind of the focus of this analysis, and it's something for which we definitely need a little bit more data, but it's kind of an interesting piece that we can do at this population scale. So we can use the new star observation, so hard X-ray colors and luminosities, to infer the likely compact object type. So these diagrams, there's a hardness intensity diagram on the left and a hardness ratio diagram on the right. And this is for M33. The black points are showing the detected hard X-ray sources in M33. The background points are actually from galactic X-ray binaries of known compact object type. And they are basically showing where you expect different types of accretors to live on this diagram. So they're marked. There's soft, intermediate, and hard accretion state black holes, pulsars, ULXs, and lower magnetic field Z and atoll type neutron stars. So we can infer what type of compact object we're likely to be looking at based on essentially its grouping in this three-dimensional hardness ratio intensity space. There are obviously some challenges with this in terms of the error bars, but it's at least kind of a first attempt at trying to get this understanding of our compact object types in a way that is kind of possible for a full population without getting the number of photons we need to do things like pulsation searches, which is challenging with current telescopes at distances like M33. So one kind of thing that we looked into was for our high mass X-ray binary candidates in M33, which of them have a hard X-ray detection that allowed for a compact object classification? And then were there any trends that we could see in terms of what type of companion star we see in systems with what type of compact object? So it was definitely a bit of a small numbers game. So I'm mentioning this as kind of one of the things we talk about in the paper, but definitely small numbers, and it would be great to get additional new star data at better depths to be able to get basically shrink these error bars down, detect all of our X-ray sources. But we detected 7 of our high mass X-ray binaries candidates in M33 were detected with new star in that survey, Jun Yang's work in 2022. And it looks like, from what we can see, the compact objects that were classified as likely black hole accretors seemed to be more common with giant or supergiant companion stars that we classify based on the SED fitting. And the neutron star accretors seem to be more common with the main sequence companion stars. But again, this is kind of a small numbers game, so it's interesting, but we definitely need more data, more numbers to be able to say anything more definitive. So I want to wrap up the talk today by talking a little bit about some ongoing and future work that I mentioned a bit at the beginning of the talk. So one piece of this ongoing work is optical spectroscopy of the high mass companion star candidates, which are so I've had two falls of observations with the DMOS spectrograph on Keck to get optical spectra for M31 and M33 high mass companion star candidates. This is very much still a work in progress, but the goal is to be able to confirm the spectral classification of the HMXB companion star candidates, because right now, as published in the paper, these classifications were done with photometric measurements. We want to be able to actually see optical spectra to confirm what type of star we're looking at. The optical spectra are also an excellent way to weed out any lingering background AGN in our sample, which are immediately obvious with the optical spectroscopy. And then also try to identify good candidates for time-resolved spectroscopy. So we do have multiple epochs of observations on the M33 HMXB companion stars. So in the fall of 2022, we got one epoch observations of the populations in M31 and M33. And then in the fall of 2023, we got 3 additional epochs on the M33 HMXB companion stars. So we're looking for radial velocity shifts, something that can kind of indicate binarity. Given the cadence of our observations, we probably won't be able to actually constrain orbital periods or compact object masses, but we could identify good systems for additional higher cadence time-resolved spectroscopic follow-up. And so again, this is very ongoing work. The data reduction and analysis is still underway, but what I'll highlight one of our really interesting stars that we are looking at right now. So here's kind of one of our HMXB companion star candidates in M33. So this is a star that is the HMXB companion star candidate. The compact object in this system was classified by NuStar as being a likely black hole. One thing I want to say about M33 and M31 is there's actually only one spectroscopically confirmed high mass X-ray binary in both of these galaxies combined, which is M33X7, which is an O giant in a binary with a black hole. So one kind of big goal of this work, and it's very much still at the early stages, is doing this additional follow-up to actually spectroscopically confirm more of these systems, have a much firmer and more detailed understanding of the systems that we can again then use to understand these different channels and types of high mass X-ray binaries that we're observing. So this star is interesting. It looks like it's an O-type star. It has strong H alpha emission. This is actually showing all 4 of our epochs of observation for the star combined, but we're in the process of trying to measure radial velocity shifts with our absorption line features, looking at the evolution of the line profile shape for the H alpha emission line, to kind of more deeply understand this system and try to kind of, the H alpha emission line, I think, is a very, very good indication that this is the high mass X-ray binary companion star that we are observing here. But again, additional analysis and probably additional time-resolved spectroscopy is needed to be able to say something more definitive about the binarity of this system. And then one other piece of ongoing work has been done in collaboration with some of my theorist friends who have released Poseidon, which is a new detailed binary population synthesis framework. So population stands for population synthesis with detailed binary evolution simulations. So this does both a detailed evolution of the stars, stellar structure, and binary evolution models, including a detailed treatment of mass transfer. And one thing I think that could be of interest to this group is we are interested in using these simulations to kind of understand the BE X-ray binary systems, which we can do because Poseidon tracks the angular momentum of both stellar components, so we can kind of see which systems are kind of at a high rotation rate that makes them likely to be BE stars. I'm showing this figure here from some work led by Davina Misra, showing the X-ray luminosity function produced by Poseidon, broken down by different types of high-mass X-ray binary systems, compared to an observed X-ray luminosity function in the red shaded region by Brett Leamer, which is using combined X-ray light from more distant galaxies, trying to match kind of our observations to our simulations in the X-ray luminosity function work. So what we're doing is trying to focus a little bit more on kind of this multi-wavelength approach. So being able to use the X-ray emission from our observed and simulated populations, compare those, but also fold in some of this optical observation, which we have in these nearby galaxies like M33. So this work, which is currently underway, we're using the best fit models that are presented in this work, MISRA 2023, to simulate the high mass X-ray binary population of M33. To kind of tailor it to be much more similar to M33, we use the M33 star formation history to weight the population to kind of match the age distribution of our observations. We apply observational constraints such as the X-ray luminosity limit, as well as magnitude limits on our observations for being able to identify companion stars. We take Poseidon produces the physical properties of the star, we convert those into the HST magnitudes and the bands that we care about, and then apply realistic dust extinction to try to simulate what we would actually be looking at in a galaxy like M33. And then from that, we can select from the simulated systems our Roche lobe overflow, detached, or BE X-ray binaries, and then compare those to our observed population. So on the left, on the next slide, I'm showing a very preliminary plot, but showing an optical color magnitude diagram comparing these observations and simulations in M33. So this is an optical color magnitude diagram. The plotted points are our observed HMXB companion star candidates presented in the 2023 paper that I've been discussing, color-coded by whether or not we have a spectrum of them, if we see H-alpha emission in that spectrum. The background contours are there to kind of just trace out the main features of the color magnitude diagram. So those are from all of the stars in this HST survey in M33. And then the colored histogram superimposed on top shows where Poseidon predicts BE X-ray binary companion stars to live in this color magnitude diagram space. So again, this kind of works to reinforce that this large clump of our observed sources are exactly where Poseidon would predict BE stars in high mass X-ray binaries would live. And we are still, working on the comparison in this analysis, including the implementation of the BE X-ray binary duty cycle, which is still kind of an open research question in and of itself, to this analysis. But this is ongoing work that we're very excited about. So to wrap up for today, talked a little bit about background and motivation. Why do we care about studying massive stars, high mass X-ray binaries in nearby galaxies? What are the high mass X-ray binary population demographics in M33, including the companion star characteristics, these age distributions and production rates, the compact object classifications, and then I talked a bit more about ongoing and future work with ground-based optical spectroscopic follow-up, as well as the comparison with binary population synthesis simulations. So I'll stop here. Thank you so much for your time, and I'm happy to take questions.
All right. Well, thank you so much, Dr. Lazzarini, for showing this really, really nice work. I see a bunch of hands clapping in the in the chat. So yes, let's open it up to questions. Does anyone? You can either just unmute or raise your hand. Yes, Andrea. Andrea, you're still muted.
In the chat, it looks like.
Yes, let's see if I can.
She can't unmute, it looks like.
Okay. So maybe if it doesn't work, you could write your question in the chat, and then I'll ask it for you, and then Dr. Lazzarini can answer. In the meantime, we can take another question while. Yes, Robin.
Yeah, so I really enjoyed the presentation today. What are the prospects of getting orbital periods from X-ray observations, either the existing ones or future observations?
That's a really great question. I think it's going to be challenging. M33X7 is an eclipsing binary, which is how it was a lot easier to do that type of measurement. I think unless we're seeing eclipsing binaries, I do think the X-ray observations might be challenging, just to get enough photons, essentially. So hopefully with, some future observatories, we can collect, more data in less time, make that type of thing a reality.
Okay, thank you.
Okay, next up I see Ken. So Ken has written a question in the chat, so I'll just read it for everyone. You connect the high mass X-ray binary production rate to the star formation rate in M33. Does it make sense, the number of high mass X-ray binaries that are being produced, and what is that number?
Yes, so we did some comparison to kind of figure out, does that number make sense? So in our total sample that is not, so we measure the total number of high mass X-ray binaries in the region of M33 for which we have the overlapping HST and Chandra data. So that's kind of the caveat. So it's kind of a number per area. We can kind of scale that up to a production rate. And then when we can compare that to other galaxies where this type of measurement has been done, which is primarily the Magellanic Clouds. We also did the same measurement in M31. These numbers do kind of fit with what we might expect from kind of seeing a slight trend with metallicity and star formation rate. We also, one kind of interesting thing is when we compare to our simulations, we're seeing, we basically weight the simulations by the star formation rate, and we're seeing kind of a similar number of high mass X-ray binaries to what we observe. So that's also kind of a good piece in that direction as well.
Okay, great. And so Ken says thanks. And Andrea's question is now also in the chat. So Andrea says, great talk. HST and Chandra have much higher error circles than New Star. How confident are you in the IDs?
Yeah, that's a great question. So, Chandra and HST, we have much more precise positions than we can obtain with a telescope like New Star. So we do that. Yeah, that's a good point. There could be a situation, for instance, where you have like two Chandra sources that are very nearby that New Star blends into one. So the compact object classification you get could be kind of a superposition of the two. I think in a lot of times for this type of New Star data analysis, we use the Chandra source positions as priors for the PSF fitting on the New Star analysis. I actually think in this M33 survey, that's not exactly what we did, but in similar analysis with what was done rather, but in similar analysis in M31, that is what we were able to do. So if you have the Chandra sources as kind of priors on where you expect to be seeing X-ray sources, you can do a slightly better job at kind of pinpointing which, looking at things like overlapping PSFs from two different nearby sources in New Star. But again, as I kind of tried to state, the New Star classifications are definitely kind of a first attempt at something like this. So it's better than nothing, but we definitely need, I think, additional data to be able to say something a little bit more firm about the types of compact objects that we're seeing in these systems.
Okay, great. So and Andrea pointed out in the chat she meant tighter error circles, which you of course got. So Ken and Andrea still have their hands raised. I don't know if there's a follow-up question, so please feel free to write it in. Oh, I guess not. Are there any other questions for Margaret? Maybe I'll use my chair's privilege to ask one last question. So this might be a slightly naive question, but I'd be interested in hearing more. You mentioned how you will be aiming to let's say, confirm the BE classification of some of those companions with the spectroscopy.
Yeah.
So I was wondering if you could say a few words about that and how categorical you think those classifications can be, and whether you already have examples of that.
Yeah, that's a great question. We don't really have examples of it just yet. I think one thing that is presents a little bit of a challenge is just seeing an H alpha emission line does not mean that we're seeing a BE star. We see H alpha emission in other types of X-ray binaries as well. It can kind of come from regions around the accretion disk of the compact object. So I think one thing that we're looking at as well is trying to see if we're looking at kind of this multi-epoch evolution of the H alpha line, as well as looking at seeing if we see any type of like shift in the H alpha line compared to absorption features, which we're pretty certain are coming from the star itself, to try to essentially confirm, is that H alpha feature part of the star or part of the compact object? So that's still a work in progress. But I think with the data that we have, we should be able to, at least for the stars that are bright enough. So some of our stars down closer to like, 22nd, 23rd magnitude, we're going to be stacking these multiple epochs together to get enough signal to noise to make a spectral classification. But I think for our brightest stars, it should definitely be possible. It's just still underway.
And maybe an even more naive follow-up question, but it's funny that you mentioned Poseidon, because a few months ago we had Kyle Akira Rocha, who gave a really nice talk.
Oh yeah.
And among other things, I think one of the things that came up was the V sun I distributions or expected V sun I distributions for the stars in high mass X-ray binaries. So I'm not familiar with the instrumental properties of Deimos, but is there any constraint you can put, let's say, on the V sun I of these stars that could eventually also help kind of present auxiliary evidence for BE stars?
They could present, the last
auxiliary evidence for the BE classification.
That's a great question. I'd have to look into that, I think.
Okay, it might be very naive, but yeah, okay, awesome. All right, any last questions before we end the session? Okay, doesn't seem like it. So once again, let me thank you, Dr. Lazzarini, for a really nice presentation on behalf of everyone. Of course, this will be also available on YouTube as a recording for those of us who could not join, due to time zone restrictions. But once again, thank you so very much. And to everyone, we'll be having our last seminar before the summer break next month. So please stay tuned. I'll be sending details of that shortly. So have a great rest of your day, everyone, wherever.
Great. Thank you
you
so
are.
much for having me.